equilibrium constants, big K, and the rate law constants, little k. Here's another thing to complain about. Okay. So before I do this, actually I just kind of do it at the top here. Before I go into the next slide, remember, just to kind of remind you how this works, if we have a system in equilibrium, you have A reacting with B to go to form, and it's in equilibrium, so we have a two-way arrow going to form two things, big C and little d, big D, excuse me. And if we go ahead and make these coefficients, these are the coefficients, right? Okay, so we can write the equilibrium constant expression. You guys have had some practice at that. Now there's a Kc and a Kp. They're very similar. Kp is in terms of partial pressures. Kc is in terms of molar concentrations. So it's always products over reactants. So it's the molar concentration of C times the molar concentration of D divided by the molar concentration of A. And they're each raised to their stoichiometric coefficient, right? Right? Okay, good. That's called the equilibrium constant expression. That's assuming everything's in equilibrium. Before I go on to the next topic, one more thing I'm going to do is I'm going to put little subscripts E's here. Okay, so those are equilibrium molar concentrations, right? All right. Well, in enters this thing called reaction quotients, and it looks like this. Reaction quotients. Instead of a K, it's a Q, quotient, reaction quotients. The little subscript C must mean molar concentrations, yep. The big thing is, and I'm going to go ahead and put little subscripts here. Instead of a little subscripts E for equilibrium, I'm going to put them, this is my 0. I'm going to put them at some time 0, at some time, at any time. I'm just going to put the molar concentration of the products raised to their stoichiometric coefficient divided by the molar concentration of the reactants raised to their stoichiometric coefficient at any time. It doesn't have to be at equilibrium. Okay? Doesn't have to. It's a snapshot. I always call this a snapshot. This is just a snapshot. Okay? It might be at equilibrium. But do you see where, if I were to, just to kind of remind you, if I were to go ahead and if we were given the same chemical equilibrium, that's the equilibrium of interest, and I said, all right, write the equilibrium constant expression, you would knock it out. You'd just go like this. Oops. Right? That's a D up there. A, molar concentration of B, stoichiometric coefficient of B. Right? That's what you would do. It's the same thing. That's my point. But this is at equilibrium. All right. So here's the deal. We can take a snapshot. We can calculate a QC, a reaction quotient, take a snapshot, and we can compare it to the KC for that same equilibrium. Okay. And if we compare our reaction quotient with our equilibrium constant, okay, we can deduce a few things. So there's 3 possibilities. I'm going to show them to you on the next slide. The possibility is your snapshot is equal to your Kc, in which case you're at equilibrium, right? Or your QC, your reaction quotient, could be larger than or less than your equilibrium constant Kc. So those are the possibilities. So here we go. A plus B going to form C plus D. Your snapshot reaction quotient looks like this. Again, you take your snapshot and you compare it to your K, or your Kc. Okay, and if they're equal, then by golly, your system is at equilibrium. It's a mathematical thing. It's a number. You compare your QC number to your Kc number. If they're equal, you're at equilibrium. Odds are, your molar concentrations, odds are you're not quite at equilibrium. And actually those two-way arrows really shouldn't be the same length. Okay? So you have 2 possibilities. One is that your reaction quotient, your snapshot, is less than your Kc. So what I like to tell students is just kind of think through it. What does that mean? If your QC is too small, then you need more stuff that's in the top. Okay? The stuff that's in the top is always going to be the products. So if your reaction quotient is smaller than your equilibrium constant, then you better go ahead and proceed to form products, and then the dust will eventually settle and you'll reach equilibrium concentrations. So that's why we say that it will proceed from reactants to products if your reaction quotient is smaller. Reactants must be converted to products to reach equilibrium. So we have QC is equal to KC, QC is less than KC, and of course the last one is your QC, the reaction quotient, is greater than your equilibrium constant. So if that's the case, if you kind of, again, look at what you got going on, basically if it's too big, you have too much stuff on the top. Okay? So if you have too much stuff on the top, of course, are the products, so the products must proceed back to reactants to reach equilibrium. So if your reaction quotient, QC, is greater than your equilibrium constant, KC, then it has to go backwards, basically. It's lopsided. So your products need to go back to form reactants again. And then the dust will settle out, and you'll reach an equilibrium. So there are some problems that go along with that. So let's do kind of a problem here, and then I'll assign 3 problems. So here we go. An equilibrium. Now don't forget that one of the rules we talked about in the part 1 in this unit was if it's a solid or a liquid, it doesn't show up in your KC expression. So don't let that catch you. These all show up in your equilibrium constant expression. But here they give us a mixture of, and you're going to want to, how do I say this? You're going to want to be good story problem thinkers. I like to kind of pull things out. So notice it says that each at a concentration of 0.002. So I might, under each of these, 0.0020 molar, 0.0020 molar. Oh, I forgot to bring my hand out. Okay, I might go ahead and throw those under there. And I think on the next slide, by the way, I'm just going to go ahead and put these as the molar concentrations at time 0. Okay, those are like those are what I'm going to plug into my reaction quotient. So we're going to come up with a QC. We're going to compare the QC to the KC. KC is given. So here we go. Plug and chug. So there's our reaction quotient expression. It's the same thing as our equilibrium constant expression. So we're going to plug in our 0.0020 in all of that stuff. And the math is kind of fun, isn't it? Because basically everything cancels with each other. So our snapshot is 1. Now remember we said that these are unitless. Actually, I should say 2 sig figs, so 1.0. So that's our snapshot. Remember 46 was our KC. So, of course, 1 is less than 46. So we said that if your small, you need more of what's on top, and what's on top are the products. So then the way this sort of problem would work, and the question, if you look back to the previous slide, what you were supposed to answer is it at equilibrium? No, it's not, because 1 is not equal to 46. And if it's not at equilibrium, which direction does it need to proceed in order to reach equilibrium? And it needs to make more products because it's too small. So reactants will be converted to products. That's it. They're kind of fun. And I'll go ahead and let you know that the problems, though, that are due Wednesday, it's not really a trick, but oftentimes instead of given the molarity, like the 0.0020 molar, you'll be given a mass and a volume. So it's like in Gen Chem 1 where you'll have to take that mass and use the molar mass to get to moles and divide that moles by the volume to get to molarity. So that's usually one extra kind of Gen Chem 1, Gen Chem 2 sort of hybrid how that works. So let's take a look at these, and I'll post these hints later, but not too much later. Feel free to tune it up. So your first problem looks like this. We have 3 gases, O2, SO2, SO3. You know, I don't know how you want to look at this. You know, you kind of read it a few times, but there's the chemical equilibrium. Sometimes one of the first things I'll do is to take that chemical equilibrium and write my Kc expression. Remember, your Kc expression and your QC expression are the same. Okay. Then it goes on to say, it gives you the volume, right? Oops, I won't do that. Okay, I guess I did. So there's your Kc expression. Notice they give you the Kc value of 100. QC is the same as the Kc, except remember Kc are equilibrium molar concentrations and QC are molar concentrations at any time, snapshot. So then my other hint is just to go ahead and proceed. You got to convert those moles to molarity. You're going to divide those moles by the volume to get each molarity. Okay, and then I say go ahead and once you have the 3 molarities, plug them in for your QC and compare it to 100. That's it. And if they're not equal, it's not in equilibrium. And actually, that's the only question here. They didn't ask you where it's going to proceed to form products or reactants, but you could go ahead and answer that if you wanted to. Okay. So compare that number to 100. The next one looks like this. It's similar, so I don't think I had to give you as many. Calculate molarity. Notice in this case you're given moles and volume. The volume is 5.25 liters. Feel free to draw a picture. In my answer key I do. Okay. So you get the molarities and you plug them in and you compare it to, looks like a 4.61 times 10 to the negative third. Remember we talked about low QCs, low equilibrium constants, sorry, not QCs, low Kcs, equilibrium constants. That means that it favors, we said, the reactants. Okay. So plug it in and then compare your reaction quotient, which you've got with those concentrations, to that 4.61 times 10 to the negative third. Blah, blah, blah. All right. Okay, the last one. Here's the tricky part. And actually, I referred to my notes to make sure that I kind of gave you good hints to this. If you read it a few times, it doesn't tell you what the mass is, but it says basically you have 2 reactants going to form in equilibrium with 2 products, and it says if the masses are equal, and I think I've seen students just pick a mass, and it works okay. If the masses are equal, then, that's grams, remember, and there's a far bit of piece to go from grams to molarity. Is the system at equilibrium? So if you consider all 4 of those gases hanging out in here, the reactants, 2 reactants, 2 products, we could come up with the mole of any of those gases by simply taking M. We'll let M be the same mass of everything times the molar mass of the, whether it's CO, H2O, carbon dioxide, or hydrogen gas. This molar mass will vary. Okay. The volume, we don't know what it is, but it's the same for everything. So you can get the molarity of each of those 4 gases by taking some M mass, which is the same, and some V volume, which is the same for everything. Take the mass times the molar mass of each of those 2 reactants and 2 products divided by the common volume. So my thought, and the way I did it on my answer key, is to go ahead and substitute for each gas, substitute in their molar concentrations based upon this sort of approach. And the hint here is since you have 2 reactants and 2 products all raised to the first powers, your masses are going to cancel. That mass term, which you don't, it's a variable, it's going to go away. Your volumes are going to go away. And you'll be left with a real live number at the end there. That will be your Q. And then they give you K. K is that 31.4. okay, and compare what you get with K, and that would be it, okay? All right. So, on to the next part, which, like I said, I'm glad to kind of do it this way. Kind of break it up. Okay. Glad we have whiteboards. So there's another sort of problem with equilibrium constant expressions. And instead of, I think in the homework you handed in, you guys told me some equilibrium constants, KCs, okay? But there's another sort of problem where basically you come up with the concentrations of everything at equilibrium concentrations, okay? So there's two different types of these sort of problems. And both the types of problems, you have to be given the initial concentrations of everything, the reactants and products. The two types of problems fall into this category. We're going to work this one today and the other one Wednesday. So if you're given the initial concentrations of everything, and if you're given the equilibrium concentration of one of your species, of a reactant or product, you can go ahead and deduce the equilibrium concentrations of everything. That's awesome. The other one, and we'll do this on Wednesday, is if you are given the initial concentrations of everything and you're given the Kc, the whole chemical equilibrium, the equilibrium constant, you can actually come up with equilibrium concentrations. Okay, so we'll do that one. That one will involve potentially the quadratic equation, which I know some of you probably love. Okay. So this is the one we're going to do today. You're given the initial concentrations, probably not at equilibrium, okay? So you could come up with a snapshot, but you really want the equilibrium concentrations. And you're given the final equilibrium concentration of one thing. And this will involve stoichiometry. So we're going to pick on this one, where nitrogen reacts with hydrogen to form ammonia in a 1:3:2 mole ratio, right? Let's see. I want to do this. Okay. So they go ahead and they say that we have an initial concentration of the two reactants, and there's nothing of the ammonia. It's a very common thing. So in other words, if you're kind of a diagramming sort of person, although I'm going to put these numbers up in a different place here in a minute, this right here says that we have 1.000 molar, 1.000 molar, and 0 molar, and that's that line is initial. Okay, so initial molar concentrations. I'm developing something called an ice chart here in a minute. Initial, change, and at equilibrium. So this down here, when equilibrium has reached the concentration of N2, right? So I'm going to find my N2, and here I'm going to write equilibrium. Very messy. But under equilibrium, I'm going to put 0.921 molar. All right, like I said, I printed out those things. I forgot. An ice chart looks like this. I really like them. I'm not going to show you on my notes this using an ice chart, but if you don't mind, let's go ahead and I like it. The way you use an ice chart is basically your columns. You have a column for everything. You have a column for each of your reactants. I'm going to put the molar concentration of N2 here, column, molar concentration of H2, molar concentration of NH3, right? I want to in my own mind, I don't always do this, but of course these are reactants, and this is a product. The ice chart, it's I, C, E, I stands for initial, E stands for equilibrium, and C stands for change. Basically, the way an ice table or whatever works is you take the initial, whatever, and we got the initial. We say apply the change, so you add it, initial plus change gives you your equilibrium concentrations. So in this ice table, it looks like we could go ahead and fill in some blanks, and all of this has to be filled out. Okay, these 3 values for everything will ultimately be filled out. So here we have 1.00 molar, 1.00 molar, nix. Okay. Equilibrium concentration here for N2, 0.921 molar. Okay. So here's how this works. Let's see what I have next. This is where I think I was going to do my, oh yeah, then the other thing, and I'm not going to, well, I can't. I usually, out to the side, I go ahead and pencil in my equilibrium constant expression. Okay, so it's the product NH3 raised to its stoichiometric coefficient, which is 2, divided by the reactants raised to their stoichiometric coefficient, which is for nitrogen, it's 1, and for hydrogen, it is 3. Okay, cool. And I can put little subscripts E's here. I know they're not usually there, but to me that tells me that's my equilibrium concentrations. That goes into my KC expression. All right. So my slides, like I say, don't use an ice chart, but let's just do this together. And anyway, if you take, this is what we started with for nitrogen. This is what we ended with. If you do a subtraction, help me out. It's 7.079. We good with that? And you know what else I'm going to do? I'm going to put a subtraction here. Reactants, well, in this case, sometimes reactants in chemical equilibria actually increase, but this one's going down. Do you see where the only way I have to go, since I don't have any product, is I have to go to form products? Okay, some chemical equilibria actually go backwards, but this is definitely a negative. All right. So, let's see, let's pick an, well, maybe not so. All right. So, stoichiometry, people, what do you think? We said in the chemical equilibria, or not the, yeah, the balanced chemical equilibria, we said that 3 moles of hydrogen, let's see, 3 moles of H2 will be used for every 1 mole of N2, didn't we? 1 mole N2, 3 moles H2. So here we go. All we got to do is then take our change, negative 0.79 molar. I'm running out of room. This is N2. See where moles of N2 will cancel? We'll be left with moles of H2. That is the change of moles of H2. Sorry, it's so messy. So basically, it looks like 0.079 times 3. I think I accidentally have. And do you see where that's going to be a subtraction too? Does that make sense? So that change is, it's really ugly here, but negative 0.237 moles per liter. Change here. Again, I'm going to put 0.079 moles per liter of N2 over 1. The relationship between N2, we have 1 mole of N2 for every 2 moles of NH3. Cool. Moles of N2 cancel, we're left with moles of NH3. So 0.079 times 2 is equal to, now this is going to be plus, because this is increasing. 0.15 moles per liter. Now if you're doing an ice table, you're almost done. Because like I said, all you got to do is you're going to take the initial, you're going to apply the change to get the equilibrium concentrations. So if we take 1.00 and subtract 0.237, that should give us, what is it?
0.763.
Thank you. And then this one, the product, if we take 0 plus 0.158, 0.158, okay, so that's it. I had to double check to see what we were supposed to do. Now, if you're given KC, you actually could check your answer. If you're given KC, you can plug these in and see if you come up with the same KC. In this case, notice the bottom that it said calculate the equilibrium concentrations, which we did. Those are the equilibrium concentrations, and come up with the value of KC. So the last slide here is going to be actually just substituting these quantities in to the expression to knock out a KC. So I like the ice chart. Okay, so this isn't worked out with an ice chart, but it kind of talks you through stoichiometry, talks you through the same thing. Okay, so that's the change. The change in the nitrogen concentration given that equilibrium concentration was 0.079. Okay. This actually is coming up with what would be the change in the concentration of the H2. Well, based upon this change and the stoichiometry between nitrogen and hydrogen, okay, you can come up with the change of the hydrogen. Okay, that's that. And then this last one is to come up with the change in the molar concentration of ammonia. Again, based upon this change and the stoichiometry of the, what is it, the 1 to 2 relationship between these two, okay, you can come up with the change of the ammonia. So you apply that change, okay, and you come up with the equilibrium concentrations we did. So this slide is basically taking this plus this, this, all to get that. Okay. I like the ice charts. So this was, after you get the equilibrium concentrations, then, like I said, you were tasked with substituting back into the equilibrium constant expression with those equilibrium concentrations, the 0.158 for the product, the 0.921, which we were given this one, right? Molar concentration of the N2 at equilibrium. We calculated the molar concentration at the equilibrium for the hydrogen gas. And it's a big, I'll say a big problem. But you see where by the time you get to this point, it's easy to actually lose track of your whole raised to the power thing. Don't forget that that's actually one of the things we learned, before break, was equilibrium constant expression raises it to the power, whichever the stoichiometric coefficient is. All right. So let's take a look at these. And I kind of set them up using the ice chart. And we'll use, if you don't use the ice chart for this sort of problem, put it this way, the ice chart will help you later on for other types of problems too. So this problem, notice it's one of those silly ones where they don't give you the molar concentration, right? They give you moles and volume, okay? So notice we have one reactant and two products. I had to make sure this was balanced. I'm like, is that PCl5 reacts to form 1 mole of PCl3 plus 1 mole of Cl2? Yes. Okay. It is balanced. So there's your equilibrium of interest. There's your Kc expression. So I went ahead and kind of set up columns for the reactant and the two products. Notice that this is kind of what we ran into before, where you have to read it a few times. The equilibrium concentrations of the products don't have to be 0. It was 0 in the case with ammonia, and it's 0 in this case, but they don't always have to be, did I say equilibrium concentrations? The initial concentrations, the initial concentrations of the products don't have to be 0, but they are here. Okay, so you can get this one, moles divided by volume. Now these, when I was doing these hints, to me, there's a lot of back and forth. So I don't know. In that, if you just look at the static hint, it's not going to make as much sense as when I do it in class. So notice that the equilibrium concentration of the Cl2 was given basically, the moles, and of course it's the same volume. You can get to the molarity of the one product. You're going to need that. Once you have this molarity, you can get to the change in Cl2. Of course, it was 0, so that is the change. And this is kind of a cool relationship because the stoichiometry is a 1 to 1 to 1. So basically, whatever this change is, that's going to be that same change because it's a 1-to-1 relationship in the balanced equilibrium. Notice that these are both positive, and actually over here, since the stoichiometry is a 1 to 1 to 1, that's also going to be the change of your reactant, PCl5, but it's going to be a negative change. Then once you got that all set up, you're ready to go ahead and find these concentrations by adding these together. Okay, add down the column. And so you were supposed to knock out the value of Kc. Once you have these 3 equilibrium concentrations, you're ready to go ahead and plug them back up into that. See what I mean by just the one picture? It'd be like kind of confusing. So for this one, we have 2 reactants and 1 product. There's the Kp expression. Okay, and notice that we're given masses and the volume, so you're going to have to do even a little more work here. Take those masses, convert them to moles, divide that mole by that volume to get molarity. Again, we're talking about, oh yeah. So you're supposed to determine the Kp. So we can start our little ice table. I already told you that. You can get to molarity from those grams. So here's our little ice table. The molar concentrations of the reactants and the product, initial change, and at equilibrium. So of course, up earlier you got the molar concentrations of the initial stuff. So here's the deal. I had to read it a few times, and if you're like me, you might too. You're like, how much S2 do we have? Well, if you read it a few times, none. You're like, is that an error? I'm like, no. Okay? So you basically have to dissect the problem. Okay, so you can get the molar concentration of H2 and H2S. There's no S2. Okay. The equilibrium concentration of the S2 is given, but just moles, so you have to divide by volumes again to get molarity. Dang it. So we know now we can go ahead and knock out the change here by difference. Okay. And since there's no product to start out with, then, wait a minute, there is product to start out with. It will actually proceed from left to right. It will proceed 2 products. So this actually would be a positive change. Okay. Then we can use stoichiometry to go ahead and backtrack what these changes are, the change in the S2 and the change in the H2. Then like we've been doing, basically we can add this to get this. And those would be the equilibrium concentrations. Of course, this one was given. So now you have equilibrium concentrations of everything. You're ready to plug back into your equilibrium constant expression. You can knock out your Kp. Can't remember the last one. So this one, they didn't give you the equilibrium of interest. Just make sure you need to balance it, right? 2 moles of ICl go to form 1 mole of I2 and 1 mole of Cl2, because that makes a difference in your Kc expression. It's always products over reactants. Notice if you read it a few times, they're back to just giving you masses again in a volume. But brackets means molarity. Sometimes students will kind of get in a hurry and start using moles instead of molarity. You can't do that. It has to be molarity. So we can get, notice that in this case, if you read it a few times, you'll notice there is no product. There's all just the ICL, no I2 or CL2. So you can get the molarity from the mass and volume of the ICL, zilch for the products. The equilibrium concentration of I2 was given, but it was given in grams, so you have to take the grams and use the molar mass of I2 to get to moles and divide that by the volume to get to molarity. So now we can actually come up with a change for our I2. Okay, and notice that this was a positive change because there was no products. The stoichiometry is kind of nice because that will be the same change for the CL2 because it's a one-to-one relationship. Okay, for the ICL you have to use stoichiometry because this is 2 moles and this 1 mole. Okay, and this will be negative. So again, apply, come down the column, take this, add the change, and come up with your equilibrium concentrations. So now you have your equilibrium concentrations of everything. You're ready to substitute back in for your equilibrium constant expression. And don't forget to square what needs to be squared. And that's it. Third of 3. Okay? So I'll push those out there and we'll call it a day.